Well, greetings, everyone. I have a show that we're at the top of the hour, and we'll go ahead and get started. Hopefully, you all, when you logged in, you were anticipating seeing the ASBI June webinar. We're beginning here at the top of the hour. I'll be doing some introductory remarks, and then we'll get into our presentation. My name is Greg Freeby. I'm the Executive Director of the American Segmental Bridge Institute. You can see my email address on screen if for any reason you should need to contact me. And I'd also encourage you to follow the American Segmental Bridge Institute as well as myself on LinkedIn. We're using LinkedIn a lot more to communicate about sort of upcoming events and activities that are happening, and also just give you some information on segmental bridges, some historical bridges that have been built, and it's a good way to kind of stay plugged in on what's happening in the segmental bridge industry. So I'll do some quick announcements before we get started. Our July webinar is the July 28th, also from noon to 1 Central Time. Mr. John Corvin from Corvin Engineering, a Hardesty and Hanover company, their chief bridge engineer, is going to join us and talk about load and resistance factor rating of concrete segmental bridges. This is a presentation John did for us with our virtual convention last year. Unfortunately, a lot of folks didn't get the opportunity to see it, so we thought we'd make that available as a recording, but John will be joining us live to do Q&A at the end of the session. So really good information about load rating. John's probably one of the most knowledgeable people in that topic, so encourage you to go ahead and register. The registration is open for that session already. The other announcement I want to share is about our 2021 convention and committee meetings in Tucson, Arizona at the Westin La Paloma Resort. The convention runs November 8th and 10th. We start at 1 o'clock on the 8th with technical sessions that afternoon, all day on Tuesday the 9th, and then wrap up at noon on Wednesday the 10th. We'll be doing our committee meetings before that on November 6th through 8th. So if you're a ASBI committee member, encourage you to go ahead and plan to attend the committee meetings, but the convention itself is open to the public. Registration is available on the website. I encourage you all to sign up and join us in Tucson in November. So some quick instructions about our webinar. If you lose connection at any time during the webinar, you can rejoin. Just use the link you have that was provided and you'll be able to rejoin. You will miss content while you're away. But so consequently, we can only issue certificates to folks who kind of meet a minimum time requirement in the session. So if you're having sort of a chronic problem with your connection, unfortunately, we won't be able to issue a certificate to you. And we have the ability to see that if people have met the minimum time they need for the session. Please allow up to a week for your attendance certificate to arrive via email. If more than a week goes by and you haven't received an email with a certificate, you can let us know. You can email me at the email address earlier, or go to the registration site where you signed up. We will do a question and answer at the end of the presentation, and I'll talk a little bit about how that works. From your desktop, you should have a little questions tab that you can click to submit questions via text. Our session moderator, Tim Berry, will be monitoring those questions and assembling them together so that at the end of the presentation, then there'll be opportunity to have your questions addressed. If you're on a mobile device, you should have a little question mark in the upper right-hand corner. You can just click on that, and again, same dialog comes up for you to be able to input questions. So with that, I do have someone saying no visible PowerPoint yet. I would encourage you to perhaps refresh your browser or come back in, because the video you should be able to see the slides at this point. They are streaming, and I've verified that they're actually available. So with that, our speakers today, we have co-speakers. Mr. Rob Bennett has 26 years of experience in construction, engineering, and inspection. He specializes in segmental bridge construction and works for RS&H. Robert graduated from the University of North Florida in Jacksonville, Florida, with a Bachelor of Science degree in Civil Engineering and is a registered engineer in both Virginia and Florida. Rob, would you like to say hello so the group can hear your voice?
Yes, thanks, Greg. I'd just like to thank everyone for attending today's session and having the opportunity to share about this exciting project in Central Florida.
Great, thanks, Rob. And then the other speaker we will have joining us today is Mr. Garrett Jones, who currently serves as an assistant project manager for Superior Construction's Southeast Division on the Wekiva Parkway Section 6 project in Orlando. He received his bachelor's in civil engineering from North Carolina State University and is a registered professional engineer in Florida. Garrett has over 9 years of heavy civil construction experience throughout the Southeast United States. Garrett, you want to say hello to the audience?
Hey, good afternoon.
Great. So with that, I'm going to turn over control to Rob, and you should have control from here on.
All right, great. Thank you, Greg. Again, thanks everyone for taking the time to join the webinar today. This is going to be a presentation on the Wekiva Parkway Section 6. It's a project update as well as a focus on the flexible filler tendon protection for the post-tension tendons. So first, let's look at our project team. The owner is the Florida Department of Transportation with participation from Federal Highway Administration. The prime contractor is Superior Construction with their main design lead, WGI. The sub-consultants they have on the project are Ranger Construction, Basilio Grogan. The segmental engineer of record is Finley Engineering. And the conventional bridge engineer of record is Arcadis. Some other partners we have on the project is Structural Technologies, BSL, who's providing the post-tensioning materials and equipment. And NRS fabricated the form travelers, which we'll be taking a look at soon. For the owner's rep, RS&H leads the CEI team. We have some consultants, Eisman Russo, Civil Site, Adaptive, and Pi. This presentation will consist of 4 parts. First, we'll have a project overview. We'll go through the design process with Finley Engineering, some of their information. We'll look at the construction progress. And lastly, we'll look at innovative materials, including the use of flexible filler. So first, for those who aren't familiar, the Wekiva Parkway is it's a large parkway that encompasses the northwest quadrant around Orlando. So it's approximately 25 miles and it's broken up into multiple sections. So today we'll be primarily focusing on Section 6, which is to the top of your screen. This is approximately a 6-mile corridor crossing over the Wekiva River, which is kind of the feature point of today's presentation. The parkway is, again, made up of multiple sections. You can see the sections there on the left that have the check mark. These sections are all completed. Section 6, which we'll be focusing on today, is under construction, scheduled to be completed early 2022. And then Section 7A and 7B and Section 8 are concurrently under construction right now and will finish slightly after the Section 6. Let's look at some details of the project overall. Again, the overall part of the Wekiva Parkway is $1.6 billion, approximately 25 miles. It's that northwest quadrant beltway that will go around Orlando. The Section 6 project is 6.1 miles long. It consists of a limited access toll facility along with a non-tolled service road for local traffic. That was very important, and the department wanted to make sure that there was a non-tolled option for local traffic. All the tolling is electronic tolling. There'll be no changed plazas along the way. It also includes a pedestrian path and trails. This area is very rural in nature, and there's a lot of hiking and trail walkers that use this facility. It was important that the contractor coordinate with adjacent Wekiva Parkway sections because we have a section on either end of the project. So that's been a real important aspect. There are 18 bridges on the Section 6 project, 3 of which we'll primarily focus on, which are the cast in place, balanced cantilever segmental bridges. There are also 9 wildlife crossing bridges and 6 bridges that are over local traffic roadways. No construction equipment was allowed in the river. We've had strict environmental requirements and compliance to those requirements on this project. And this project was designated as a design build contract method. You can see the corridor largely runs east and west, about an hour north of Orlando. Now Garrett's going to talk a little bit about their relationship with Finley and some of the elements of design.
Okay, again, good afternoon. I'm going to discuss some key elements of the design process and introduce a few acronyms along the way that some of you may be unfamiliar with. As Rob mentioned, Finley Engineering Group out of Tallahassee, Florida, is the design partner for the segmental portion of the project. Per the project RFP, or the request for proposal, the design build team was required to provide an IPR, or independent peer review, at the 90% phase submittal and the final submittal for the segmental bridges, which fell under the Category 2 bridges in the PPM, or the Plans Preparation Manual. The IPR was intended to be a comprehensive, thorough verification of the original design. The project team is also utilizing the ERC, or the Electronic Review Comments System, to track the entire review process, both comments and responses, for plan reviews and project submittals in a database. All comments and responses reside in one location, allowing any user easy access to all or partial review on demand. The system allows project managers to easily track all comments and responses from all reviewers and consultants at any time during the process. The design build team also utilized BRIM, or Bridge Integration Modeling technology, on the Wekiva 6 project to integrate both design and construction drawings to enhance visualization of complex details with 3D graphics and colors. This modeling approach takes the next logical step in the use of 3D visualization and advanced engineering software to integrate bridge information databases into the planning, design, construction, maintenance, and inspection processes. Finley used the models created from the BRIM workflow to generate parametric shop drawings that would update with every approved modification required. We were also able to use the models on site to assist in rebar placement.
All right, thanks, Garrett.
The Wekiva River bridges consist of a westbound and an eastbound bridge as part of the tolled State Road 429 Beltway and a non-tolled bi-directional bridge for local traffic. As seen in the typical sections, each bridge includes 2 12-foot travel lanes and wide shoulders with the ability to accommodate additional lanes to the toll roads with future expansion. The local service road also includes a 12-foot sidewalk for viewing of the pristine Wekiva River. The segmental superstructure of each of the 3 bridges is comprised of 2 38-foot long pier tables, 10 16-foot long segments extending downstation and upstation from each of the 2 pier tables, and 2 70-foot end spans that bookend the segments. 3 closure pours between 8 and 9 feet in length join the elements together to complete the full 880 feet in length. So we'll go through a little bit of the foundation and substructure and then get into the good stuff. The 3 Wekiva River bridges accounted for 641 24-inch square precast concrete piles that ranged anywhere from 40 feet to just over 100 feet in length for a total length of 40,000 feet in piles. All of the substructure concrete placements fell under the mass concrete category, and temperatures were continuously monitored using wireless sensors that provided real-time data to ensure that the concrete cured properly. This included the footings, columns, and caps. Each of the footings for the transition piers were approximately 150 feet in concrete, and the footings for the 6 main piers averaged roughly 450 cubic yards. The design build team included the use of tree shapes in all piers at the Wekiva River bridges to fully capture the preferred theme of the celebration of trees on the river's edge. We included that as part of the aesthetics package in our technical proposal. The columns for the segmental piers averaged 38 feet in height for a volume of 160 cubic yards. The caps cast at the transition piers served as the shift between the approach spans, where you can see the fib 78 girders in the background, and the segmental spans that begin with the end span. The caps averaged 170 cubic yards in volume, divided out over 3 lifts. The addition of the multi-rotational pot bearings underneath the end spans and the finger joints at the top of the caps allowed for movement between the 2 superstructure types. The cast-in-place pier tables were supported on false work designed by Finley, as seen in this slide. The false work included support brackets on both sides of each column, with transverse and longitudinal beam assemblies separated by sand jacks that enabled us to adjust the stringers to the correct elevation for decking. The pier tables were cast in 3 lifts. Lift 1 was the bottom slab. The second lift were the walls and the diaphragms, and then the top slab for the final lift, for a total of approximately 400 yards. Again, the pier table spanned 38 feet in length with a 7-foot offset away from the main span over the river as part of the balanced cantilever erection method. Self-launching travelers were erected on top to cast the segments in each direction. The end spans were also cast in place on top of false work, as shown here. We used 6 24-inch diameter pipe piles in each location, with a similar transverse and longitudinal beam assembly that was decked out with stringers. The end spans were completed in 3 lifts as well, for a total of just under 400 yards per location. Each end span was just under 70 feet in length and was constructed on the multi-rotational pot bearings to allow for movement. As far as the segments, each of the 3 bridges included 40 segments, with 10 downstation from the pier table and 10 upstation from the pier table on each side of the river. The depth of the segments and the base width both varied in dimension from segment to segment. The top deck remained a consistent 60 feet throughout each bridge, and all 120 segments were cast in 16-foot lengths. Due to the variability in the shape and size of the segments, the concrete volume ranged from 120 yards at each pier table down to 80 yards towards the end spans and the midspan.
All right, thanks, Garrett. As we discussed the cast in place balanced cantilever method, one integral part of that is the form traveler, which you can see in red. The form traveler really enables this type of construction method, and it was chosen due to the fact that there was no equipment allowed in the river, so no bridge foundations. So to really achieve that 360-foot span across the river, this was one of the sole construction methods to achieve that. So looking at the form traveler, it's made up of different components, as you can see in this schematic. There's a bottom support, which holds the weight of the concrete and the reinforcing steel. And then there's the top support, which supports the top deck. It has variable level work platforms also for the workers. From the side view, you can see on top, there's an A-frame. These particular travelers have two of those frames. They're commonly referred to as the horses. And these are what support the overall weight of the segment and the traveler itself. The longitudinal beams in the background are projected forward, and this allows the traveler to move forward or backwards, providing the aspect of self-launching. That way you don't have to have any equipment underneath or above to facilitate this casting. Now we're going to take a look at a short video that sort of graphically depicts what goes on during balanced cantilever construction. All right, thanks, Greg, for showing that video. Hopefully everyone got a better idea now of the balanced cantilever cast in place construction method. Moving on, we're going to look at some progress update photos. So last year at about the same time, this presentation was given as a 2020 update. So what we thought we would do is keep the 2020 slides and then sort of show a contrast with 2021 so that the audience can see the progress that's been made in the past year. So this photo was taken about a year ago with our drone, and you can see the form travelers there in red. There are 2 pairs of them, and they're casting segments for the westbound bridge, which will be part of the toll facility 429. On the right, you can see the service road bridge. The construction is already completed, and it has 2-way traffic, again with that pedestrian walkway on the right-hand side. The middle bridge, construction had just begun for that bridge, and the pier tables were under construction at different stages there. So moving forward to this year, you can see now this photo is looking east, and the westbound bridge is largely completed. All the segmental work is completed on that bridge, and the eastbound bridge is nearing completion. Again, this photo shows the 4 form travelers that are casting segments opposite of the pier, with only several, I think at this time there are about 8 segments remaining. So this photo, again from 2020, shows the progress. This photo is looking sort of mostly to the west. You can see the end span segment at the bottom of the photo being constructed. At this time, as Garrett mentioned, that is constructed in 3 concrete lifts. So the second and third lifts are being worked on there, reinforcing steel being installed. Now this is the 2021. So you can see all the pier tables are complete. The segments are being cast in either direction with only a handful of segments remaining. This is a good shot of the river underneath, again from 2020. You can see the broad spans of this main span and the fact that there's no intrusion into the waterway with this construction method. In the photo from 2021, currently, all the pier table work is complete. There's some little bit of patching and rubbing going on the westbound bridge to your right, and the eastbound bridge is being continued construction. This is a good shot of the false work for the pier table that's being constructed. Some of the contractors refer to that first level as the dance floor. So this is a good shot of that. It's kind of the beginning phase. And then now, of course, all the pier tables are complete and construction is winding up at the river. This photo shows the progress in 2020 as we're coming into the main span closure with approximately 32 feet left to be constructed. And this photo was just taken several days ago with approximately 25 feet until this main span closure, till the 2 tips of the cantilevers meet. So now let's look at some project innovations that we're using. Again, I had mentioned the aerial drone. We're using a DJI Inspire 2 is the model that we're using there in the photo on the right. We have multiple licensed operators that have completed their drone pilot's license and registered with the FAA. We also use a wireless weather station that we have mounted on the roof of our office trailer. This connects to a Bloom Sky app that everyone has on their phone. It'll show you a real-time photo of what the sky looks like, as well as temperature, wind speed, humidity. So that's been very useful to have on the project. If you are away from the project site, at any time you can click on that app and it'll show you what the conditions are, which is very helpful. Central Florida, especially in the summertime, we get these big thunderstorms that roll through. So it helps everyone stay connected with what's going on. In 2017, we implemented the use of wireless tablets, iPads, and Samsung tablets on the project. This allows the inspectors to do their field work electronically. They can also utilize digital signatures. We didn't realize how important this was going to be until 2020 hit, and we were encouraged to not hand off paperwork from person to person. And so the fact that all our inspectors were already using this type of technology was very beneficial and helped us comply with the safety regulations. For survey control, along with the conventional equipment that we have, we're also using a GPS rover. The one we purchased was a Topcon Hyper-V. An advantage to this is it's a one-man independent GPS receiver, and so it's very low manpower, and it's very easy to go out and check curb line. We can check drainage structures and other elements on the project.
On the contractor side, Superior utilized the DOCA Paratop overhang system to form the bridge decks at the river and also at some of our wildlife crossing bridges. Unlike typical overhang jacks, this modular formwork system came pre-assembled in 20-foot sections and included the overhang jacks, decking, and handrail. The benefit of the increased production far outweighed the additional material costs. We also used the tie bot to assist with the rebar tying for the bridge decks. The tie bot looks much like a bidwell and is set up to self-locate, self-position, and self-tie up to 1,100 rebar intersections per hour. This allowed our subcontractor to continue tying rebar in other areas of need. Wireless turbidity monitors were placed on the north and south side of the Wekiva River bridges to provide real-time turbidity numbers should the river become impacted by construction operations. The KMZ data files were overlaid onto Google Earth for planning purposes. Each section or phase of the job was added as a layer that could be turned on or off so the project team could analyze what could be built as time progressed.
All right, another project innovation that we have was the requirement to have fully replaceable post-tension tendons for our continuity or bottom slab tendons. So one way to achieve this was by using a flexible filler material instead of a cementitious grout. So flexible fillers have been used in Europe and other areas and other industries for years. These materials may include wax, grease, or even a type of silicone gel. But for this project, the FDOT specifications required the use of a microcrystalline wax that's used to protect the post-tensioning strands in these bottom slab or continuity tendons. It has about the consistency of peanut butter at room temperature, but when it's heated up, its viscosity is similar to that of water. So where is flexible filler used, and what is microcrystalline wax? It's a derivative from petroleum. It's homogeneous, hydrotrophic, and has a strong adhesion to metal. So those properties make it a valuable protection material. The FDOT Structures Design Guide lays out where flexible filler is to be used. And they specify that it's be used in the bottom slab continuity tendons and segmental box girder bridges, post-tension tendons and I-beams and U-girders, any vertical strand tendons, as well as horizontal tendons and post-tension piers. And here you can see several graphics of how the material behaves and the different construction types there. So before Superior could start to use flexible filler in the bridge, the specifications required them to construct and fully fill mock-up tendon. So they submitted a full plan on how to achieve this. To the right, you can see the schematic. Oops, sorry about that. For this tendon mock-up. This is 200 feet long. It had a vertical difference of 10 feet with a change there in the elevation. And this was very important because it gave the contractor's personnel a chance to work with the material for the first time. There was only one or two other projects in Florida that had used flexible filler, and so it being such a new material, it was good for everyone to gain experience with this. So here you can see the scale of this full-size mock-up. Just to give you an idea of the magnitude, this was a large undertaking and took several months for the contractor to complete. So one of the specifications requirement was that the tendon had to have force on it. So they wanted the strands to behave the same way in the markup that they would in the bridge. So if you just laid strands in there and they laid on the bottom of the duct, then that wouldn't really be reflective. And so they did require force to be applied to this 19-strand tendon. And again, it took about 3 months for the contractor to complete this work. So once the tendon was filled with flexible filler, the next stage was to cut up the duct in various locations and analyze if the tendon was full, if we had any voids, if we had any air bubbles that were produced as the result of injecting this material. But there had to be a lot of thought given on how to remove these portions of the duct. If this was a grouted tendon mock-up, then the contractor would just go out with the gas-powered chop saw and they could just cut it up in various locations. The problem with flexible filler, though, if you took that same approach, you would heat the material as you're cutting through the strands and you would begin to mobilize that filler, and so you wouldn't end up with an accurate picture of what the flexible filler was in its environment at the time it was filled. So for this reason, the contractor had to use a small circular saw that was a low abrasion cutting saw, enough to cut through the duct, but not to heat the material. So the stages that it was determined that removal would take place was first to remove the inlet and the outlet pipes, checking those to make sure that those were full of material, and then to remove the caps at either end. So the caps were both fully filled, which was a positive sign. You can see how the wax kind of took the shape of each one of the cutoffs of the strand in the adjacent photo. The next stage was to cut various windows in the duct to observe how the flexible filler filled the tendon. So again, what we want to do is be careful how we removed these sections. This mock-up was performed during the summer, and that black HDPE duct would reach about 125 degrees in the sun. So we made the decision to remove any of the portions that were in the top region of the mock-up. So that would be section cuts A, B, and C. And then after we had a chance to observe those, then we would cut the bottom portions, B and D. So here are the photos of what the wax looked like when we were able to remove those portions of duct. They were full in each location, which was a very positive sign for the team. You can see how the wax sort of encompasses all parts of the strand, and that was really valuable for protecting the tendons. So our mock-up conclusion was that yes, this mock-up, it was a complex profile, but again, we didn't want to just go out and lay a duct on the ground. We wanted something that would mimic or mirror what was going to be flexible filled in the bridge. That's why this profile shape was chosen. Also, we realized that it was important to vent both of the caps, both on the inlet side and the outlet side. Even though you're using the vacuum assist on the outlet, it's important to vent those caps so that you don't have trapped air. Also, we learned that at the inlet side, if you have a small leak, that you can quickly stop that leak using ice cold water and ice cold rags. So in the end, the mock-up was a success. We had several engineers down from FDOT's central office from Tallahassee, and some observed the filling of the tendon, and then several others observed the autopsy or the cutting and removal of duct. So now looking at the tendons in the bridge, now the mock-up has been completed and approved. You can see the tendons on top are the cantilever tendons. These are used largely to support the construction loading. These are still filled with grout because they're in the top slab of the segment. However, the continuity tendons, which are bottom slab tendons, these are the ones that were filled with flexible filler. Here's the profile sheet from the plans that shows the profile of those bottom slab tendons. For these, you don't have very much of a change in vertical differential. So we weren't real concerned with getting any voids in these, and these filled relatively quickly because of their short length. We also had the continuity tendons that are external. These are HDPE duct tendons that are inside the box of the bridge, and these are the drape tendons. These are the ones that we had to make sure that we had no voids or no trapped air during the filling process. Garrett, you want to talk about some of the equipment that's used in flexible filler?
Sure. So the next couple of slides give an idea of what equipment is needed for the flexible filler operation. Superior set up a flatbed trailer to move the equipment around as needed. The trailer included 4 510-gallon tanks that hold the flexible filler, as seen in the picture. The holding tanks were equipped with a heating system capable of producing a melted wax free of lumps within the temperature limits specified by the project specs. The system applies a uniform heat to the wax to avoid locally high temperatures that may damage the wax or the container itself. Each time we injected, we were required to have 25% more than the total quantity to fill the duct and anchorages, discharge at the outlets, fill the pumping equipment and hoses, and still maintain an approximate 10% of wax in the holding tanks during the operations. The end of the flatbed held the pump with all the necessary connecting hoses, valves, and pressure gauges. The pump had to have sufficient capacity to ensure that all the ducts can be filled and vented in the allotted time specified by the manufacturer and spec. The pump maintained the same pressure of at least 75 psi as it was injected. It must also be outfitted with a valve that can close off the flow to the system once the injection was completed. Specs called for a positive displacement pump that could provide an injection of filler into the duct at a range of 40 to 70 feet per minute. Once all the equipment was installed on the flatbed, we had a certified electrician come out and install a panel box for us to run all of the equipment. A vacuum pump, you can see a picture of that on the right side, was required on the outlet end for assisting with injection or for filling in voids that were at incomplete wax filling operations. The vacuum came equipped with a volume meter for measurement of void volume, as well as a flow meter to measure the amount of wax being injected. It was required to have a minimum capacity of 10 cubic feet of air per minute, with the capability of removing 90% of standard atmospheric pressure within the PT system. As far as personnel on site, DOT specs required that the contractor conduct all wax injection operations, repairs, and inspections in the presence of the filler injection foreman, the filler injection QC inspector, and the engineer. A PT system vendor installation technician certified by the vendor as having sufficient knowledge and expertise to oversee the operation was required to be present for all activities for a minimum of the first 2 days. Superior chose to certify our foreman, 2 field engineers, and 2 additional members of the crew. To give you an idea of the flexible filler quantities for the Wekiva 6 project, we included one of the tracking sheets for the service road bridge. All 3 bridges had similar tendon layouts and quantities. Those shown are for flexible filler only, and these quantities do not include grout. So the length of the duct for the bottom slab and peer-to-peer tendons came out to a little more than 8,100 linear feet, or more than 24,000 linear feet in total for the 3 bridges. Between the 619 and 622 systems that were used, the total length of strand came out to 162,000 feet per bridge, or just under 500,000 feet total. And then the volume of wax used was roughly 3,300 gallons for a total right at 10,000 gallons. And just keep in mind that each of these quantities were theoretical and did not include waste. So we had a little bit more of the duct, strand, and wax.
Thanks, Garrett. So what testing is required for this flexible filler wax? Well, really the only requirement is you're taking the temperature at the inlet. You're also trying to predict at what rate is that wax going to cool as it travels through the duct. If this was a grouting operation, you have multiple tests that have to be run for flowability and wet density and unit weight. But because the wax comes as a pre-manufactured product, you simply heat it up, check your temperature, and start injecting. The lessons learned, I would say, on our side is that the heated wax flows much faster than grout. As Garrett said, 40 to 70 feet per second. So, you know, on a 150-foot tendon, you better be ready when they switch the valve on to start pumping. Also, the heated wax will leak from a much smaller hole than grout will. So during the air test prior to filling, even if you meet the specification requirement for the amount of air loss, we found that you have to address any leak, no matter how small, because so that you can avoid any problems during the filling operation. Also, in the winter months, the wax would cool quickly as it travels through the duct, and we're in Central Florida. So I can only imagine if the project was in Minnesota or Michigan, you know, you would probably have to take precaution using either heating the internal box itself or using heating blankets or bands around the outlet part of the duct to ensure that the wax doesn't set up too quickly. Also, we found that if a small void is discovered in the post-filling inspection, that you can simply heat up a small amount of wax and pour it in the inlet or the outlet, because the wax is a reversible process, unlike cementitious grout, which is a little more involved using a vacuum grouting operation. Here, we purchased an infrared camera as we were working with the flexible filler material. What we wanted to do is to try to pinpoint any cool spots in the duct after the filling operation was complete. So as you look at the photo on the right, you can see that the tendon, once it was full of grout, that duct there measured 139 degrees, with the adjacent concrete being in the 50s. So this probably would have been a January or February operation. And we would use the camera also to track the progress of the flexible filler as it's traveling through the duct and try to ensure that we didn't have any cold spots along the way.
So I listed a few comparisons here when looking at wax versus grout by the numbers. When comparing wax per gallon to grout per cubic foot, wax is about 2.5 times more expensive per volume than grout, just for the product itself. On the other hand, there's much less waste when using wax than grout. A lot of this has to do with the testing. As Rob mentioned, the only testing required for the wax was the temperature at the inlet. So as the wax is heated to meet this requirement, it's circulated back into the tank, so no material is lost. With grout, if a bad batch is made for whatever reason, that batch must be discarded and you must start again. Grout also requires a certain theoretical volume to be batched per tendon, and whatever's left must be discarded. There is no waste with wax in this instance because there is no mixing. Wax is also injected at a rate of 40 to 70 feet per minute, as we've said a couple times, and grout is about half that. So the waxing process is about twice as quicker per linear foot. So from a contractor's perspective, with lessons learned, the biggest lesson learned is to try to avoid at all costs injecting during the winter or the colder months. Temperature played a big factor, and the wax cools rapidly as it goes through the longer ducts. The minimum testing also assisted in the greater production versus the grout, as time wasn't lost in the initial stages of the process. Another item of importance is ensuring that you maintain good working equipment. This was quickly learned in both the waxing and the grouting operations. Grouting equipment is much more readily available for rent or purchase. With the flexible filler, we were limited at the time to just the purchase of the wax equipment. As the product becomes more standard in the industry, I'm sure the equipment will as well. One item we added to our wax injection operations plan that was not included in the DOT specs was to bleed all of the outlets after the wax reaches the vacuum end. We noticed during the initial mock-up that the vacuum continued to pull the wax away from the ejection end, which actually resulted in the cap at the injection end not being filled. So that's something that we changed up in the operations plan. We also found that in the event voids were detected, like Rob said, they were much easier to repair than with grout. For wax, we simply located the void, tapped into the location, and poured the heated wax into the void until it was filled. It's not listed in this slide, and technically it's not a lesson learned. But one thing I do want to point out that we were very fortunate to achieve was consistency within our PT, stressing, grouting, and waxing crew. For a job that started in October of 17, about 4 years ago, we've been able to maintain the core crew for the duration of the project. And considering the shortage of quality labor throughout the country and with COVID hitting us early last year, the ability to keep a crew together is something that you technically can't measure, but has been a huge benefit, is worth noting. So with that said, that wraps up our presentation on the Wekiva 6 project update and the flexible filler tendon protection. At this time, we'll take any questions you may have.
Thank you, Garrett and Rob. We do have some questions, and I will ask Tim Berry, our moderator, to unmute and serve as our moderator during the questions. There was one question I saw that I'll address, and that is about the video. And yes, that video is available. If you go to our website, there's a tab for videos, and you'll find a link there to that video. So it is available. The other thing I want to let folks know, I just put it up in the chat, is a link to an Aspire magazine article about this project that was written when the first phase was completed. And so if you want to read a little more information about the project, that I'd encourage you to grab that link out of the chat to take a look at the article. So with that, I'll turn it over to Tim.
Thank you, Greg, and thank you to Rob and Garrett also. Really, obviously interesting project. Not surprisingly, generated a bunch of questions about the flexible fillers. We'll get to those in a second, but I did want to address a couple that were not related to that. First of all, you'd mentioned that you basically had no access from below because of the environmental restrictions. So how were the form travelers removed after you were completed with the cantilever? Were they launched all the way back?
Yeah, I can take that one. We back launched them back to the pier table and kind of disassembled them in the opposite manner of which we assembled them. One thing we did differently between the second and third, as opposed to the first and second bridge, is we kept a lot of the pieces together, and we were able to fly the form traveler over in sections. It actually cut out about a month's time per each side of the river, as far as disassembly and then reassembly for the next bridge. So yeah, we back launched back to the two piers.
Okay. How many sets of form travelers did you have for the whole project?
Or 2 sets for each side of the river, one upstation and downstation.
Okay. Thank you. What was your total cycle time for basically launch to launch when you at your peak, when you got beyond your learning curve?
So I would say between all 3 bridges, at this point, we have 3 segments left out of the 120. A good cycle time, we got down to about, I would say, 9 days average, including the learning time at the beginning. We were affected quite a bit with COVID. I would say about 11 to 12 days was an average cycle, but once we hit a good rhythm, we were consistently doing 9, sometimes 8 days.
Okay.
Yeah, especially on this third bridge, you know, like Garrett said, once they got over the hump of COVID last year and were really able to hit their stride in the third bridge.
Okay, the tie bot that you mentioned, I've seen that around. I wasn't familiar that it was being used on this project. Did you see a significant time savings by using that?
Time savings, yes. The biggest thing for us is, like I mentioned, it enabled the subcontractor to take the 8 to 10 guys that they would have tying rebar on the deck, and go tie a column or a cap or work on the next segment. So there was a time savings there in the overall project. For the tie bot itself versus manual labor, there was a small increase. I wouldn't say a large increase, but it just helped move on to the next thing. One thing I will mention with the tie bot is it works really well if you plan ahead for it. With us having the DOCA overhang system, we were able to deck out ahead of the tie bot, and it helped out there. If you're consistently waiting on overhangs to be stripped from the previous deck pour and the tie bot can't jump out in front of you, then there's not much savings, cost, or time there. But if you plan ahead, it's a very beneficial product, specifically using the DOCA system with it as well.
Gotcha. Okay, interesting.
And just one more note on that, Tim,
yeah, sure.
is that the tie bot was primarily used on the wildlife crossing bridges, where we had over 3,000 foot of just pretty much flat slab bridges, conventional construction, and then it can really, you can really see it's increasing the production as it's working in that environment. It was not used in the segmental portion of the job.
Right. No, that's good clarification. Thanks, Rob. So I had a question in the chat. What was the time between the casting of a segment and the stressing of the cantilever tendon?
I would say about 12 hours typically. The transverse tendons would be stressed first, and then the cantilever tendon. Sometimes it would be the next day, so 24 hours, but sometimes they're able to do it once they got the approved concrete break. Is that your recollection, Garrett?
Yeah, for the first bridge, the service road bridge, we were always stressing the next morning, and then we went back to the drawing board to try to see if we could reduce the casting time. So we started pouring earlier in the morning. We would finish about 5 or 6 o'clock, and then that afternoon around 2 or 3 o'clock, we would start breaking cylinders. And once we got our strength, a lot of time we were able to stress that same afternoon.
Okay, great. I think you may have mentioned it, but just I guess probably good for clarification. What were the temperature limits, and I guess the window for using the flexible filler for injection? What was the high and what was the low that's recommended?
It was the range was between 212 and 240. We tried to shoot for the higher end, just because once you start injection, specifically in the winter or the colder months, the wax cools off pretty rapidly. So we were shooting closer to the higher end of the 212 to 240 range.
Did you run into any issues with it cooling at the, especially for the longer tendons at the end opposite of the pump?
A few times, yes.
Okay. And what was the pressure? I know you went over it, but if you go one more time, just what was the pressure using and the target pressure for injection?
The minimum was 75 psi.
Okay.
That was at the duct inlet, and then 145 at the pump.
So we had a question, pretty interesting. I know you talked a lot about ambient temperature and some of the effects that you saw, and of course you're in Florida. So if this were to be used somewhere else where you'd have potentially, cooler winters, this is maybe just a guess, but did you come up with a target or a minimum ambient temperature that below which you really just couldn't make it work, or you would have, issues?
To my knowledge, we never ran into that, but like you said, we are in Florida. It does get cold here for about a week, but not cold enough where we had issues with not being able to inject. Like I said, we did run into some issues with it cooling off pretty rapidly for the longer tendons, but we never ran into any temperatures where we just could not inject. So as far as a threshold for what that would be, I'm not sure I have an answer to that. Maybe Rob could.
Yeah, we never established, a specific temperature at the site. I do think if you were using this product and, for instance, in Virginia, many of the concrete placements, the environment is heated so that you can place concrete during the winter. So I think you would have to use artificial heat in the same way to heat the environment, or maybe use heating blankets, or they also make heating bands that if you're using flexible filler that comes in a 55-gallon drum, you could wrap the tendons on the close to the outlet. You could wrap those in those heater bands, and to assist the flowability of the wax.
Does the manufacturer have a limit on the high end for, like, if you had a cooler temperature, could you heat it, heat it higher before you start pumping it to try to not lose as much heat? Is there? I'm sure there's probably a limit that the manufacturer recommends.
There is. It depends on which manufacturer you're using. Superior use the Fuchs wax, and their product data sheet has the upper end temperature on there that you wouldn't want to exceed, but I think each manufacturer would be slightly different.
Gotcha. Okay.
Yeah, their product data sheet said that the flash point was 425 degrees, but
wow. Okay.
with our DOT specs, I mean, we couldn't even get close to that. So
okay, gotcha. Was there any special method for finding voids? You had said, that was part of obviously the inspection. Is there anything different for looking for voids with this material?
Not really. I mean, the post filler inspection is similar to what you would do with grout. You remove your inlet and outlet tubes. You also remove the tubes and the valves that go into the cap. And then you just observe those. You don't have to drill in to these tendons, obviously, because you have a flexible material like you do with the grout to do bore scope inspection. But you can utilize the scope or a pin, flashlight to observe if the cap or the tendon is full at that point. We also use some strand to sort of make sure, or tie wire on the first ones to make sure that we didn't have just a little lens of wax and then there would be a void behind there. And we never saw that. Kind of like if you had a cup full of water and you have a leak in your cup, where's the void going to be? It's not going to be at the point of the leak. It's going to be at the top of the water level, in essence.
Okay. So were there any special safety precautions that the workforce had to utilize working around this high temperature material?
much like the grout, we wore the Tyvek suits. Just make sure everyone's got those on. Depending on what station you're set up at, if you're at either the injection end or the outlet end, make sure you got your typical PPE, your gloves, your glasses, a lot of times face shields. So pretty similar to what you would do with grout.
Yeah, the gloves that they used were the heat resistant, like a welder's type glove. And one difference with the flexible filler is that all your inlet and outlet pipes are metal instead of being the flexible tubing like you have with grout. So handling those handling the hoses or handling the, you know, those pipes, it's essential that everyone wear those heat resistant gloves.
Okay, just wanted to follow up on one of the comments from earlier about, you know, the cooler temperatures, and we were prompted that this material and this technology is used in other countries, including France, where they, you know, obviously they have cooler temperatures than we do in Florida. So I think the overall message there is it is something that can be used in cooler temperatures. You know, it's not going to work only in a Florida environment. So there are ways to handle cooler temperatures, and it is something that has been used in other areas. So it wouldn't be something that would prevent it from being used in different environments. So Greg, I believe we have run through all the questions. I don't know if you had any to follow up, or if anybody else.
I think that I'm with you. I think we addressed all of the questions, and so we've run just a little bit long, which appreciate those who didn't have a hard stop and could stay with us on to the conclusion of the Q&A. I will again remind, if you'll allow us a week to get you your certificate of completion for those who are getting professional development hours for participating in today's session. If you have any questions or comments about the session, you can pop an email to info@ASBI there, as you see on the screen. And also just a reminder to follow us on LinkedIn. You'll get updates about upcoming webinars as well as other activities that are going on across in the segmental industry. So with that, I will go ahead and close the webinar and say thank you again to our presenters, Rob and Garrett, and also to our moderator, Tim. Appreciate you all joining us today for today's webinar. And I look forward to everybody coming back for our July webinar on load rating of segmental bridges. So with that, we will close the webinar. Thank you, everybody.
Thank you.
Thanks.